Hi, everybody. Our next presenter is Seth Meldon, and Seth represents Progress Software, where he focuses on the Corticon business rule engine and its use in real-world applications. This is Seth's third presentation at DecisionCAMP, and we bring him back because he usually shares very interesting real-world cases. Not theoretical considerations, but something what they actually did using rule engine and what was complexities, issues, and how they resolve them. So I don't expect Seth to talk about ChatGPT or other generative AI things, but rather he will describe a case study that deals with risk mitigation analytics in energy infrastructure. Seth, go ahead.
Thank you, Jacob. So yeah, I am a solution engineer focused on Corticon, as Jacob described, and I'm going to talk a little bit today about a use case that has developed and, well, that we encountered, and ultimately Corticon was selected and now is up to a production environment specific to a field that coming in I knew much less than I probably should have as a working in the software field. You'd think you might know more about how electricity works, but I really didn't. Especially with respect to just kind of how power gets delivered from where it is produced, ultimately transmitted to where it goes. And I think what at kind of in a snapshot view of why this presentation is not going to cover the dreaded ChatGPT variants is the very fact that the biggest, the first and foremost issue that one would bring to the table with respect to using any sort of tool like that is the explainability of it. The more that things can go wrong, the more that one needs to be able to explain why that went wrong, why the decision was made in such a way that ultimately produced something quite bad, whether that be medically, financially, or in terms of infrastructure. So this is just kind of it'll talk a little bit here about things that I didn't know. Hopefully I won't be too redundant for people who do know how electricity gets to your home. But essentially, the main thing that we're going to be talking about today is specific to how Corticon is being employed for risk mitigation and essentially evaluating priorities for the maintenance of some of the most complex machinery there is, which are large power transformers. So when electricity is produced, whether from a power plant or from a renewable source, you can see on the left-hand side there that it comes out at one particular voltage, but in very layman speak, what you need to know is that those power lines that you see that kind of look like ski lifts over long stretches of land, which look distinct, at least in the US. I know if there's any folks in Europe where you have your infrastructure more effectively implemented underground, which probably would have been nice in retrospect for the US, but here we have lots of power lines, and those big ones are very different than the power lines that ultimately wire into your home, be it underground or through a power line above ground, because the efficiency with which you can transmit electricity over long distances is far greater when you are transmitting it at a higher voltage. So what that means is transformers are used. Transformers, we'll get into what they are, why they're relevant here, but transformers are ultimately going to be used to step up, so to speak, is the nomenclature used. A step-up transformer will make it higher voltage, make it easier to transmit over long lines. Step-down transformer will then ultimately make it so that those power lines can be better, it can handle a lower voltage, which is appropriate for home electricity needs. Now, this is all infrastructure that is across any country, largely maintained in the same way, or largely regulated and maintained in the same way that utility companies in general are regulated and maintained. So it's kind of an amorphous public-private sort of, while regulated, these are private companies and therefore not, therefore at the end of the day, our client that we ultimately work with here and anywhere else are going to be profit motivated, which is something that, I mean, it's not the most comforting thing for the people who are managing the safety of these things, but likewise, it's interesting to think about what drives the sort of investments that are not regulatorily mandated and which are not ultimately going to be revenue producing. What those are going to be things specific to maintenance of very complex machinery that's very expensive, difficult to replace, specific to transformers in this case. So in their simplest form, transformers are basically, I'm going to try to use these laser pointers too, are essentially two different cores, or excuse me, two different coils of wire around an iron core. So those two different sides of the coils are going to ultimately transmit from one side a higher charge, and using electromagnetism, we're not going to go much deeper than that, will electrify the secondary winding over here, the secondary winding through the core, by not even having to touch these circuits, which, if you remember in science class growing up, kind of that's one of the main ways that you initially create a circuit. But for lots of reasons related to safety and efficiency, what's unique about transformers is this can all be done with electromagnetism as opposed to touching two wires together. One of the key things that you need to kind of bear in mind is obviously the deathly level of electricity and being involved here, but also we're going to get into just how many things can go wrong that need to be considered in the ongoing maintenance of these. So large power transformers, I mentioned, are the ones that will be seen in like substations, which are very common sites around the US. So you probably are familiar with those sorts of stations, and what those are doing is largely that step up and step down process that are necessary for similar to kind of when a freight train will bring its cargo in one mechanism and then ultimately deliver it to a grocery store to be sold on the shelves with a different delivery mechanism, depending on kind of the supply chain that is most efficient. Same idea, although a little bit more high stakes with electricity. So you very well have probably heard some of the headlines as just over the years, as far as just mainstream media playing up the threats of potential threats from adversaries to just the literal physical being that are these substations. But even outside of that, there are tons of things that can result in a lot of different negatives as far as the longevity of how long these transformers can be used for, which is pretty important considering that 90% of the electricity across the US, I'm going to try to not be so American-centric here, but for the sake of, I'll narrow it down and say that our client that we worked with was in the US, and we have lots of power lines here. So these are very expensive, and because you can see just the average age of just large power transformers, which are distinct from, say, the ones that you see at the top of power lines in your neighborhood, these are larger, hence the name. These are much more expensive, much more difficult to replace and maintain. And so it's very much a major operational cost that needs to be invested in to make sure that you're getting the most life out of these very expensive pieces of machinery that have lots of downstream effects where a lot of things can go wrong by a lot of different metrics. Now, I mentioned a little bit of the cost and the downstream effects, but also the besides just the actual threat of somebody pulling up and shooting a gun at a transformer, which is not that uncommon. There's quite a set of literature on how to address things like a snake that mistook something about a transformer for prey and ultimately electrified itself and caused all sorts of problems. Same with rodents, various different aspects of storms. So even if the supply chain was great in every aspect with respect to the delivery of new and maintaining the parts for these transformers, it would still be very expensive to do so, to replace them and treat them poorly. Add in the fact that there are so many different parts that post-COVID and even pre-COVID, obviously we're very backed up with supply chain woes, as well as just very dependent upon internationally manufactured. So most of these components are not created in the US nor any specific country. They need to be conglomerated like most pieces of machinery do. So we need to take into consideration one more risk besides those weather, besides the cost, but also just the availability of parts. So kind of what I'm hoping to contextualize in this snowballing bit of anxiety as far as all the things that can go wrong with a transformer that I've laid onto you is just to talk about how much needs to be considered and the extent to which it is quite useful to be able to quantify what would otherwise be seemingly subjective risks to the long-term shelf life, so to speak, of these transformers, such that we can maximize lower costs, not exploding neighborhoods, not producing hazardous chemicals in the water supply. A lot of things can go wrong that will have a lot of negative impacts for a lot of people if we don't trust our utility companies to sufficiently invest in risk mitigation strategies for these transformers. So now let's kind of hone back in on the specific components with which we're going to be building the rules out in this case, and hopefully in more to come, wherein we're going to be kind of categorizing those different risks, almost similar to risk matrices that are probably more common for the audience in just the insurance space all over, whether that be life, home.
Unmute yourself.
Someone in
Okay.
the audience muted me. Hopefully I didn't say something offensive to produce that.
No.
So
Go
we
ahead.
have two different categories that we're focusing on here. The threat assessments, which we're going to drill into, as well as the health. So kind of as it sounds, things that basically measuring for and evaluating the risks of everything that could possibly go wrong as far as externalities on the right-hand side, and everything that is in the best interest of the owners of these transformers to manage, measure, log over a series of time in order to get a good grasp on kind of the trajectory of the lifespan now and in the future of these transformers. So one of the things that I liked, or that's unique about this set of problems, which is not new and not a unique problem to solve, obviously, we're only talking because of electricity here, is the way in which this particular client and the partner that we worked with really wanted to not have, I guess this can kind of have a tie-in again to disparaging LLMs, but not have a set of sensors on all of the different power system machinery that are going to accumulate a whole bunch of data, every bit of data that can possibly accrue, in search of a practical application of that data, versus really by leveraging rules that are completely not intertwined with the data being gathered, we can surface what is most important, what is most critical to address, as opposed to just hoping and employing just more generalized statistical probability functions of that kind of looks like it might explode, we should hone in on that, versus using more highly defined sorts of algorithms for kind of even things like the types of gases being given off by a transformer and the various different parts that can be tested about it. So specifically, I use the word how critical it is to replace, and that's literally the word of the day here. Criticality assessments is, as defined here, really the relative importance of something that could go wrong. So if we think about it in terms of life insurance, if someone skydives, that's probably going to have a major impact. If I have a beer once or twice a week, and I tell the insurance adjuster that, they'll probably be okay with that to an extent. But skydiving is going to have a larger effect. Similar in terms of the sorts of weighting that we're going to be leveraging here, which is not made up it's not subjectively determined based off of this client. These are things that, again, this is a ubiquitous problem to solve, and there are lots of ISO standards and general sort of regulatory frameworks and measurements that are guided from the top down and can optionally be employed by utility companies to measure the effectiveness and criticality of the current state and kind of time series data of the transformers. So again, not regulated in such a way, which is curious, but also if you just again consider all of the potential downstream impacts and costs to replace of these pieces of machinery, it's not the sort of thing that they're going to necessarily want to underinvest in as a utility company. This is kind of just illustrating more and more of the aspects of criticality, where we even get down to things like the power grid, and if the last time you had a power outage at your home because of a storm, perhaps there wasn't, but moving forward into the future, some of the determinations that are involved in those cases is who do we care about most as far as who needs to get this situation addressed and resolved in the shortest order of time. Probably the hospital that has lots of people on respirators that are on a time-limited generator for power is going to be more important than your residents in the eyes of the public, the utility company, and just in terms of what the opportunity cost of not having electricity is. So that was the criticality side. On the health side, which is the other, again, just the status check, again, we can start to think about things that are more inherently quantifiable as far as just the number of different tests, measures, and evaluations against kind of what the out-of-the-box functionality of a transformer, as far as the output of voltage, of wattage, of these sort of hazardous materials that it generates. We need to be able to compare against what's called the nameplate specification. So literally just the nameplate on the machinery that says this should be producing this amount of electricity, but also as compared to a time series of data collected about that object, about that piece of machinery within the context of that substation, and perhaps even things like this particular substation's proximity to other things within the area. Is it a neighborhood, or is it an abandoned airfield, for example? So this is a delightful, easy to read, very simple little graphic that demonstrates kind of at a very high conceptual level, what needs to be accounted for. And this is just the health side. This is the more quantifiable side, where it's literally the outputs of measurements of particular risk factors, such as the dissolved gases produced by oils within the transformer itself. Now, this is, as you are probably building together in your head, pretty much every single string of text there, every single little box is made up of many different rules underlying them. These are all ultimately going to be weighted factors that are going to contribute to essentially decision-making now, planning for the future, and really the ranking of priority for what to do when and how urgently. Then combined with those other factors outside of the context of that specific discrete transformer, but moving into the side of the potential regulatory impacts of something going wrong, the availability of spare parts, the mean time to repair when we do have a technician and the parts available. That's all going to be a secondary calculation to this already rather convoluted set of calculations. Now, one thing I wanted to, that I thought was a interesting kind of thing to dwell on a bit in when we were developing this, but also to talk about here, is there, by virtue of just how many different things have, how many different components of this machinery, even just on the health side, have very specific tests, very specific measures, with not easy to generalize sort of inputs and outputs. So we'll get into a couple of the rules, specifically one of the most convoluted one, which is dissolved gas analysis. I'm going to actually skip ahead real quick to that just to illustrate it. This is one of the, I think it's about 12 different, 12 different measures that go into just the health component of the health and criticality evaluation for these rules. So this is just one, and try to think about how even this being the one kind of sample size of rules that needs to be implemented, how can a data model be produced in such a way that we're not going to have overly explicitly defined data fields for, like, I don't want to have necessarily a specific data entity called total dissolved combustible gas, and underneath that keep track of specific fields of acetylene measure, of carbon monoxide measure. So perhaps I want to go in the direction of generalizing to specific tests, specific measurements, and specific gases. So now we add into that, this is one of those more just kind of, there is a calculation to be done here. There's a right answer based upon this combination of values. But now we add into that, besides just kind of these observable gases being produced, we can move into things that are even more convoluted, like specific test measurements. Obviously, in here, we also see things combining data from the last time we checked this transformer versus the nameplate, in addition to just kind of what the difference is between now and the nameplate, and what the difference is between now and the last time we checked it. So how can we establish a data model that is going to really solve everything without being too overly verbose, without really kind of negating the benefit of abstracting into a common model all of these rules? So this was a slide that I presented to the client in kind of illustrating this, because these are electrical engineers by and large, not software engineers. So data modeling isn't a day-to-day activity, but it's easy to illustrate how things can get rather convoluted and quick and difficult to maintain if we go with something on the right-hand side versus something more generalized to the greatest extent possible on the left-hand side. All of those different individual fields being maintained individually is going to make it much harder to kind of have a easy to build upon set of rules that are reusable across different domains, across different substation calculations, et cetera. So we kind of had a happy medium between the two of them. So I'm going to go ahead. Yes.
Seth, can I ask you, this was very interesting table with rules, table 1. Can you show us also later your actual executable tables?
Yeah. So yeah,
this one.
Yeah. So I'm going to go ahead, into what that is specifically measuring. That is
okay.
This first component. There are two different tiers of this first measurement, and this is the first. Again, you can see by me talking over myself and correcting myself that there are lots of different hierarchies of tests and measurements, and the order of events and the ways in which that those different tests and measurements impact each other in order to ultimately produce a digit with 2 decimal points for a risk variable that will ultimately define what to do from that point forward. So I apologize for overlapping sort of my vernacular here, but This is one of the most important aspects of measuring this dissolved gas analysis, aka the oil analysis. So there's suffice to say that there is different types of oil that is used for the insulation between the different components of the transformer in order to mitigate issues of safety, but also to maximize the efficiency with which the electricity moves from one component to another, and ultimately out at a lower or higher voltage. So a lot of this is all related to measurements that can be derived about just the oils being produced and given off by a transformer through a number of different kind of test mechanisms. So let's get into how we can kind of try to implement this in such a way that doesn't have every single last data field being explicitly defined, having some degree of a common data model being leveraged here. So I wanted to kind of give the full picture as far as what is involved in just one of these rule sheets. Granted, it is one of the more complex ones that are being used. So it's not going to be too crucial that you understand all the vernacular that Corticon uses for developing these rules. Really, all you have to know for the sake of today is this individual decision table looking sort of thing is called a rule sheet. And all of the different conditions are going to ultimately produce any number of actions down here. The conditions are defined by dragging in from our data model that we've defined, assigning when this particular data field meets this particular value or conforms to this range or is indeed less than 30, along with all these other things, then we're going to assign the value down here. Now, within Corticon, what we've done here is basically assigned aliases for all of these different measures within the context of this rule sheet so that I can use this kind of common field measure and delineate between them in terms of being able to define which of these gases I want to have a more common sort of thing that's called a measure, but I want to delineate that measure first to identify the fact that I'm working on the insulating oil analysis. Second, to delineate between the gases that are being used for this total dissolvable combustible gas, because not all these gases are combustible. There's exceptions here and also just supplementary calculations being involved within these rules themselves. So here, using these aliases, I have just one data field, these specific measures. And I'm going to click into what you're seeing here is just this plain natural language view of in place of all the different pieces of syntax across these filters and the specific scope of values and just kind of the plain language description of what's happening within this condition row. I can have that natural language equivalent. So now when I toggle that off, we can see how I have assigned an alias to one specific measure that will represent all cases of dissolved gas analysis. And that is going to be defined based off of the case where measure.gas measure, its value is going to be found within this list of strings. So if indeed I have a measure that conforms to the filters, that is going to be things related to that dissolved gas measure, but also be specific to the type of gas that is indeed combustible or dissolvable, as shown down here. We're able to have a much more concise data model being leveraged while being able to leverage that same data model in very unrelated sorts of calculations beyond just dissolved gas analysis, but also reuse it for the sorts of tests that can be produced. In the interest of time, I'm going to go into just the last section I have here, which is going to generalize, roll up into what it's called the rule flow, which is kind of as it sounds, made up of all of the different rule sheets, as you saw a moment ago, organized into a series of events, basically. So here I have this group of rule sheets organized into a rule flow. So these are all the criticality related rule sheets over here. That will then be fed into the health related rule flow, which contains rule sheets, again, related to just those health assessment rules themselves. And finally, as I mentioned, we have a very arguably underwhelming output, which is really just going to be a value for how important it is to take a look at this particular transformer. And depending on its the outputs of all these individual calculations, we can drill down into specific measurements related to any of these various different considerations. Finally, this is, I think, a good kind of reminder of something that I said at the onset as far as the explainability of this. So with Corticon, this is just a glimpse of one other assets that we work with called the rule test, where we're, again, using that same data model on the left-hand side, dragging and dropping, matching the same hierarchy defined in the data model. So pulling in an assessment, pulling in two different indices underneath that assessment that are uniquely identified by this field index name. This is health. The one up here is going to be criticality. And then I collapsed all of these other index components because just the one that we covered a moment ago is its own index component identified by that dissolved gas analysis alias. And you can see how I have all these different measures, and really these are all unique identifiers for the sake of being able to have rules specifying how these different gas measures relate to one another without, again, having an entity named 2-foul furans PPV. That would be a bit too verbose. Finally, let's say something does, well, one of the benefits that we have in being able to build these rule tests is by running kind of the input and just producing the output as we see here, also optionally measuring. See, I put in an expected value under the expected column of a health score of 1.145, and it'll highlight any cases where the expected does not match. But likewise, I can see the precise order of events across all of those different steps. So there's, you can see here, this is actually the rule flow that gets deployed. There's 190 individual rules across all of this. And we can see only the rules that actually fire over the course of this test, precisely what happened in what order of events, what that data field looked like before, what it looks like now. So I scrolled all the way down to show how that kind of final step there is going to overwrite the ultimate index score by virtue of having combined the health and the criticality scores, ultimately adjusting what was previously within that one execution of the decision service 7142 to now be 1.142. But this is going to be very valuable for the sake of isolating where something could be not in line with our expectations, with what is going to be a safe level of anything. If I were to say double click on any one of these rows, it'll take me directly to whatever rule produced that output. And so it is about as explainable as you can get for a very complex set of calculations that are otherwise quite convoluted and difficult for novices to get a grasp on. But this has been successful as far as this individual utility company. And obviously, this is not a, again, unique use case, and it's not a problem that is in a vacuum specific to this one client or partner. So we're hopeful to identify more and more opportunities to implement what we're doing here. Briefly, the actual where this fits into the actual solution is this utility company has thousands of different assets like transformers. This is not going to be running in kind of a somebody has the idea, how's that specific transformer doing? It's going to be on a recurring basis, firing off from various different sensors of these transformers. Again, not just accruing data for the sake of accruing data, but performing these calculations and storing the outputs of those calculations so we can see not purely how the difference of the gases being measured differs from this month to last, but also the rate at which the criticality score might be producing concerning outcomes. So we can really drill down into specific units, and that's being fed into various different analytics and visualizations tooling for this ultimate broader solution. So I'll leave it there. I promised I'd be as concise as I could. I realized there was no lunch break, so hopefully can leave some time for you to step out for some lunch, but I'll also open up for questions.
Thank you, Seth. Any questions to Seth? Just unmute yourself and ask question. Well, people thinking, I want to ask you, is this system actually in production? And what is your deployment platform, if it is?
Yeah, it is in production within a subset of their transformers thus far. So you may, if you're familiar with Corticon, these rules can be deployed to a server, or they could be generated into a serverless function with JavaScript. This is a server-based deployment. However, it is a whole workflow defined using a serverless sort of architecture. Specifically, Azure functions are defining a kind of a recurring series of decisions and data integrations wherein on scheduled basis, it's passing in data being pulled in from a Snowflake database, then passing into the decision service elsewhere hosted on Azure, and logging that back into Snowflake, and again, having that time series of data available for seeing how things are degrading or not.
Questions? Considering complexity of these rules, I wonder who actually maintains these rules and make changes in the rules, business people or developers or Carticon consultants?
Yeah, so we did no consulting here, and they haven't really taken advantage of too much free consulting of mine either. It took a few training sessions, but I mean, also just bear in mind, like, this is the terrible looking combination of rules here. Like, this is their day-to-day that they were coming from and working with Excel within. And so it's, I mean, everything can look simpler when compared to something that looks like that. So it's not the simplest thing, but these are also electrical engineers for whom a lot of this vernacular is not going to be new, and it's easier to pick up when it's a domain that you already are an expert in.
There is a word exception here. How this exception is implemented in the last rule?
Yeah. So actually, I don't know if that was captured or not. So what basically I can just speak to it. These are all producing. So the AND statement is basically going to be captured within multiple, like when we have one specific column with lots of different values, that is effectively just an AND. So in order for this outcome to be produced, all of those things have to happen. So actually, I can see now that that's why we have one outcome being produced here for that value of 3, because it was the value of 3 that had the AND, whereas these ones are this or this. So if this or that, then that's why we have 2 different 2s. In the case where there was anything in conflict, what we're doing here is when we'll ultimately choose what is the worst performing score out of all of these. And then, so in order to do so, we're establishing values for this particular measure. Sometimes there might be the dissolved gas rate might match this, but also the measure over here matches over here. So we're taking the worst score, which is going to be the lowest score. So ultimately, after having produced all of those outcomes, then we'll measure to determine what is the worst one and use that for downstream.
Okay. Okay, I don't see any more questions, and but I see Mike Parrish here, former Carticon expert. Mike, do you have any questions? Or do you see progress with product? No? Okay, in this case, thank you very much, Sam, and I want to ask you at the end only, says only one thing. This table looks very interesting for decision management community challenges. Mike Parrish used to provide a lot of challenges himself. Maybe you can convert this to small decision model, and this is format what really attractive to give people as a challenge. So we can see how different vendors can implement this tool, and you can provide the first solution in Corticon. Okay?
That's good.
So send it to me. Okay, thank you very much. And
Thank you.